This lecture deals with section 8.7. This is on Taylor series. So we talked about power series in the last video lecture. Today we're going to talk about a specific type of series called a Taylor series. So let's start with a definition. A Taylor series is a representation of a function using an infinite series it is of the form f of x equals sigma n goes from 0 to infinity of the nth derivative at some value c over n factorial times x minus c to the n. So you can see here any function, any continuous function, differentiable function, continuously differentiable function, can be represented as an infinite series of polynomial terms of the function itself. So if we were to expand this out, let's look at what the first term would be. The first term is when n is 0. So here, this superscript is dealing with the derivative of f. So it's when n is 0, we would get the 0th derivative of f at some value of c over 0 factorial times x minus c to the 0. Plus, when n is 1, we would get n to the first derivative of f, so f prime at c over 1 factorial times x minus c to the first power. The next term would be the second derivative at c over 2 factorial times x minus c squared, and so on. Okay? So we can actually do a little bit of simplification here. This would be the 0th derivative of f is just f itself. So that would be f at c. 0 factorial is just 1, so we don't have to write that. And x minus c to the 0 is also 1. So the first term of a Taylor series is just the function evaluated at this c value. Plus, f prime at c is just f prime at c over 1 factorial, so that would be f prime of c times x minus c to the first. Plus, the third term here would be f double prime at c over 2 factorial times x minus c squared. Let's think about what that next term would be. So we just follow the pattern. This would be the third derivative at c over 3 factorial times x minus c cubed plus so on and so forth. Okay? So the beauty of this is that any function can be represented in this following way as long as the function is continuously differentiable. Okay? So we note here fn of c is the nth derivative of f evaluated at c. C is called the center of expansion, and if c is 0, then this series has a special name, then the series is called a Maclaurin series. Okay. So only if C is 0, we have its special Taylor series, basically. Okay. So let's try an example. Find the Maclaurin series for the function f of x equals e to the x. So what we want to do is just follow this formula with c equal to 0 because it's a Maclaurin series. And we'll just write out several of the terms there. Okay. So let's start. If n is 0, we need the 0th derivative at c, right? So we can actually make like a little bit of a table here. So let's do that. So fn of x, we'll need to evaluate at fn of c, and then multiply that by over n factorial times x minus c to the n. Just make a little table here. So if n is 0, we get the 0th derivative of x, 0th derivative of f of x, well, that would just be the function itself. So that's e to the x. Let's evaluate it at c. In this case, c is 0 because it's a Maclaurin series. So what's e to the 0? That's just 1. And then let's assemble this term here. So we have our fn of c, which is 1, over 0 factorial, times x minus 0 to the 0, which is just 1 as well. So our term, 0th term, would just be 1. If n is 1, this is the first derivative of x. So what's the first derivative of e to the x? It's just e to the x. What's the first derivative evaluated at c? C is 0 again. So the second term would be 1 over 1 factorial times x minus 0 to the first power. Simplifying this, we just get x. If n is 2, it's the second derivative of f, so it's just the derivative of this guy here, just e to the x. Evaluated at 0 is again 1. And then assembling this, if n is 2, we get our derivative evaluated at 0, which is 1 over 2 factorial times x minus 0 to the second power. So what's this? This is just x squared over 2 factorial. Okay, let's do one more term there. 3. Okay, so the derivative, third derivative, would be e to the x again, evaluated at 1. And we'll get 1 over 3 factorial, x minus 0 to the third, or x cubed over 3 factorial. All right, so let's get our Maclaurin series going. So we know that based on our Taylor series formula, f of x is equal to the infinite sum, n starts at 0, goes to infinity, nth derivative at c over n factorial x minus c to the n. So e to the x, that's our function, is equivalent to the infinite sum of all the terms that we have listed in this column. So 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus, based on this pattern, what do you think the next term would be? Well, the last two terms kind of give it away. The next term would be x to the 4th over 4 factorial, then x to the 5th over 5 factorial, and so on and so forth forever and ever and ever. So this means that the e to the x function can be represented by this infinitely long polynomial function. Okay? So let's take a look at what that looks like. Okay. So here's our e to the x function. We know that that looks like. It's pretty simple. Now let's look at the terms as we add them. Okay, so let's say if we just use the first term to do the approximation, that would be y is equal to 1, right? So you can see here that the y equals 1 is a very terrible approximation to e to the x. But if we add another term to it, if we add the second term, let's say we add x to it, we see that it becomes this line. Still a pretty not very great approximation to e to the x. Let's continue to add terms here. Plus x squared over 2 factorial. So now you can see if we have the three terms of that Taylor series, it's kind of starting to bend towards the e to the x function, right? Let's add a couple more. X to the 3rd. X to the 3rd over 3 factorial. So you can see as we add those terms, the curve, that our blue curve, starts to approach that e to the x curve. So if we continue to do this ad infinitum, you can see that the Taylor polynomial starts to become the e to the x function. So all infinitely many terms, it'll take infinitely many of them to continue that. So you can see after only about 5 terms, we get a really good approximation for the e to the x function using our Taylor polynomial, right? Of course, it's not equivalent unless we have all infinitely many of them. All right, so let's try another one. Let's try the sine function. So let's look at the Taylor series. So we'll find the Maclaurin series. For f of x equals sine x. Okay. So we'll do this in a similar way. Let's make a table. So we're going to do our n's, our derivatives at c, our derivatives generally, and then we'll evaluate each of them at c. And then we'll assemble the terms and then we'll simplify them here. Okay? So let's do a few. Oh, and by the way, we can actually represent this as a summation if you notice the pattern. This summation for the previous example is x to the n over n factorial. Right? This is like x to the 1st over 1 factorial, 1 over 0 factorial, and so forth. X to the 0. So you can see that pattern. We can condense this into a sigma notation here. Okay. All right, so if n is 0, we get the 0th derivative of our function, which is just the function itself. That would be sine of x, right? And we might as well just get all of our derivatives here. So what's the derivative of sine? Is cosine. The derivative of cosine is negative sine. The derivative of negative sine is negative cos. And of course we could do that forever and ever, but we'll try to get the pattern based off of our first 3 derivatives there. All right, now we need to evaluate these derivatives at c. And what is c here? C is 0 because this is a Maclaurin series, okay? So the Maclaurin series, the center is 0. So we plug in 0 here. Sine of 0 is 0. Cos of 0 is 1. Sine of 0 is 0. And cos of 0 is 1, so this guy is negative 1. Let's do one more. Oh, let's do 2 more. How about that? Derivative of negative cos is sine. Derivative of sine is cos again. Sine evaluated at 0 is 0, and then 1. So you see we get some alternation in the sign. We have some zeros there, okay? Right, so let's look at our first term would be 0 over 0 factorial, x minus c to the 0. Second term would be 1 over 1 factorial, x minus c to the 1. And 0 over 2 factorial, x minus c to the 2. Negative 1 over 3 factorial, x minus c to the 3. 0 over 4 factorial, x minus c to the 4. And 1 over 5 factorial, x minus c to the 5. So you can see here, this is going to be 0. It's 0 times all this stuff, so the first term is just 0. Second term would be 1 over 1 times x minus 0 to the first power, so this is just x. Next term would be 0. Then we get negative x minus 0 to the third, so that's just x to the third over 3 factorial. Negative x to the third over 3 factorial. Next term is 0. And the last term is positive x to the 5th over 5 factorial. So the sine function is equal to the sum of all of these terms. I'll just skip the zeros, so that would be x minus x to the third over 3 factorial plus x to the 5th over 5 factorial. Now let's guess some of the terms that we see with this pattern, right? So we're going to have some sign alternation. It's going to be positive, negative, because of the alternation of the derivative sign. So the next guy is going to be negative. Now if you notice, this is going to be x to the first over 1 factorial. Notice that as we increase, we have to skip over that even-powered term because every time sine, it gets back to the sine function, which is every other derivative, we get a 0 when we evaluate at 0. So we're going to skip over that x to the 6 over 6 factorial. We won't have that. So the next one would be x to the 7th over 7 factorial. Then the sign's going to alternate again. We'll have x to the 9th over 9 factorial. And it'll alternate again, x to the 11th over 11 factorial. And so on and so forth forever. Okay. So the sine function is approximated by this infinite series here, which we can condense into a condensed summation notation. Let's say the sum n goes from 0 to infinity. Now we're going to have some alternation in the sign, so we need an alternating term here. And the first one is positive, so we can just say n. And then we have all the odd powers here, so it's going to be x to some odd power over the same power factorial. So recall how we get an odd power. We do 2n plus 1. 2n plus 1. So let's just make sure that's right. So if n is 0, we get x to the first over 1 factorial. That's our first term. If n is 2, if n is 1, we get negative 1 to the 1, which would be a negative. 2 times 1 plus 1 is 3, so that would be x to the third over 3 factorial. We get the second one. When n is 2, we get a positive. 2 times 2 plus 1 is 5, so that's that term, and so on and so forth. So this is the condensed sigma notation for our sine function. We can take a look at that in Desmos as well. So let's look at sine of x, and let's see how well we approximate here. Alright, so if we just use the first term from our series, it's just x, right? X minus, the next term is x to the third over 3 factorial. So you can see that x doesn't really approximate it, but after the first term, we get a good approximation on this interval here, and then it kind of falls off. We add our second term, or excuse me, our third term. It's x to the fifth over 5 factorial. You can see we get an even better approximation, and so on and so forth. So we're going to do the next couple of terms. We can see that the approximation to the sine function gets better and better. So if we just continue this ad infinitum, we see that that polynomial curve is exactly equal to the sine curve. Okay, pretty neat. Okay, let's do another example, but this time let's go for a different center. Okay, so find the Taylor series. For f of x equals 1 over x, centered at x equals 1. Okay. So let's do our table. It's an easy way to do this. So 0, 1, 2, 3. We'll see if we can't get them. Okay. Alright, so when n is 0, it's just the original, so 1 over x. What's the first derivative of 1 over x? Well, that's like x to the negative 1, so negative 1 over x squared. The derivative of that is positive 2 over x cubed. And the derivative of that is negative 6 over x to the fourth, and so forth. Okay. Now in this column, again, we are going to get to evaluate at C. That's the center of expansion here. We're centered at x equals 1. So we're going to plug in 1 to all the derivatives and see what we get. So put in 1 here, we get a 1. Put in 1 here, we get a negative 1. 1 here is 2. 1 here is negative 6, and so forth. So here our terms are going to be 1 over 0 factorial times x minus c, which is 1 to the 0. This guy is going to be negative 1 over 1 factorial, x minus 1 to the first. 2 over 2 factorial times x minus 1 to the second. negative 6 over 3 factorial times x minus 1 to the third, and so on. Alright, so if we look, this is 1 over 1 times 1, which is 1. This is going to be negative 1 times x minus 1 to the first, so negative x minus 1. 2 over 2 factorial, well, 2 factorial is 2, so 2 over 2 is just 1 again, so this is plus positive x minus 1 squared. And here we have negative 6 over 3 factorial. Well, what's 3 factorial? 3 times 2 times 1 is also 6, so that's going to be negative x minus 1 to the third, and so on. So 1 over x is equal to the sum of all of these terms here. So 1 minus x minus 1 to the first, plus x minus 1 to the second, minus x minus 1 to the third. Now let's guess a couple more terms here. So you can see we have some alternation in the sign. So the next one's going to be plus. And you can see it's just adding an extra term with an extra factor there. So the next guy is going to be x minus 1 to the fourth, minus x minus 1 to the fifth, plus so on and so forth. So if we collapse this into a sigma notation here, let's say n goes from 0 to infinity, we're going to have some alternation in the sign. First one's positive, so let's say n negative 1 to the n. And then you can see all the terms are x minus 1 to the n power. Of course, the first term would be x minus 1 to the 0. That's true here. Okay. So this is the Taylor series representation of 1 over x. Of course, if we were to just plug in these terms into Desmos, we would see that it approaches the 1 over x function pretty nicely. Okay. Alright, so that does it for Taylor series. You can go ahead and get started with your assignment.